Well, welcome to 1.5. We're going to look at two different place value systems that you actually use every day without even knowing it. And the first one is a base 2 system, and it's known as a binary system. And it uses the digits 0 and 1. And the place values are the powers of 2. Our system is a base 10 place system with digits 0 through 9, and the place values are all powers of 10. So again, you want to read the book first, and don't worry about if you understand everything, but it gives you some background. So I'm going to go right to 1.15a, and we're going to take a look at the place value system here, and then we're going to look at these numbers in base 2 and convert them to base 5. Base 10. Okay, so here is our base 2 number system. It's the same as base 10, only it's 2, powers of 2. 2 to the 0 are 1s. 2 to the 1 is itself. 2 squared is 4. 2 to the third power, which is 2 times 2 times 2, is 8, etc., right? So we want to find out what this number is in base 2. Now, I'm not going to have you even memorize this stuff. I'll give you a base 2 just like this here on a test and ask you this question. What number is this base 2 number in base 10 in our number system? So the way I recommend doing it, you got 4 1s and 2 zeros. I'm going to go backwards this way. Okay, so I got 4 1s and 2 zeros. That's the number. So I have 132 plus 116 plus 18 plus 14. So this number is 32 plus 8 is 40, 60. So this number in base 2 is 60 in our, as you know, 60. So let's try this one. 10101. See, 10101. 10101. Okay, I laid it in. So I have 116 plus 14 plus 11. So that is 21. And that is how your computer actually represents 21. Because your computer is base 2. Well, example 1.16 just flips it. It gives you base 10 numbers and asks you to convert them into base 2 numbers. Students that miss problems on the test, this is where they miss them, all right? So I would pay attention. I would actually read 1.16. It gives you 2 good examples. And I am going to do 1.16a. And I'm going to do it right now. So here's the one with 80. We're going to transform 80. That's 80. No subscript down here, right? So that's our number 80. I'm going to translate that into a base 2 number. And this is the one you might want to watch this a couple times, right? I'm going to do it for 80 and for 2. So for 80, I'm looking down. I'm going to start up here. I'm looking down here to see if I can find 80 or something close to it. I can't use one of these because that would be 128. I can, however, use one of these. That's all I have, one or none. So I'm going to use one of these, and that's 64. So now I've got 80. I can take away 64 because I've already accounted for 64 of them. And that leaves me with 16 left. So I can't use any 32s, and I can use 116. See that? And then, so if I'm going to use a 116, subtract 16, and I'm really done. The only thing is I have to put zeros into my other place values. If I don't, this is not going to be the same number, right? I've got to hold my place values. So 80 is 101 followed by 4 zeros. 1, 2, 3, 4. And I'm going to put a 2 there because this is a base 2 number. So our number 80 is equivalent to this number in base 2. Now the other one in base 2 we're going to do is a 2. So how do I write 2 in base 2? Our number 2. So I'm going down here and trying to find it, and there's a 2 right here. So I want one of those, and I want none of those. So I can write that as 1, 0, base 2. So that's not a 10. That's 1, 2, and 0 ones. Okay, well this is the read in your book, but I'm going to go over it a little bit because it's pretty important. Note that binary, which is base 2, is the most economical place value system in terms of the fewest digits required. Only a 1 and a 0. That's all we use. That's the setup. But the price for this economy is a lot of bits, right? We can represent 803 with 3 digits. There they are. 1, 2, 3 digits. But in binary, it requires 10 digits. Each digit is called a bit there. The reason computers use binary numbers is that it's related to logic. 1 is true, 0 is false, and they can build a huge system with this sort of idea. And also, it's related to electricity flowing through a wire. 1 means the wire is hot or on, and 0 means the wire is off. So if the wire is on, if there's electricity in it, it's on. If it's off, it's off. We could use base 10 numerals to represent electricity flowing through a wire, but the problem is it would require components sensitive enough to differentiate between these different voltages over and over and over again with no interference from all the other wires and voltages. So that would be tough. It could be done, but it would be tough. This system is really logical and it's very, very, very reliable. So it's much easier and more dependable to build components that simply look for voltage on or voltage off in any given wire and turn this digital signal into binary numbers, right? A single character text requires 8-bit number. So that's 8 different numerals for just like the letter A to encode it in computer memory. An 8-bit number is known as a byte. And if you look at your computer, it probably has maybe terabytes of memory. So computer scientists, because it gets really cumbersome, developed a base 16 system. And we're going to look at that now. Well, a base 16 system is going to require 15 numerals. So what they did, after 9, they used A to represent 10, B to represent 11, C is 12, 13, 14, and F is 15 in base 16. So all we're going to do is the same thing we did with base 5 and base 2 and base 10, is take a base 16 number and rewrite it as a base 10 number. And so there's two examples here you can look at in your book, which I advise you to do. But I am going to do example 1.17a. So here is our base 16 system. And again, anything to the 0 power is 1. Anything to the first power is itself. 16 squared means 16 times 16, that's that, 16 cubed, etc. So there's our basic system of base 16. So here's a base 16 number, and I want to translate it into a base 10 number. So I'm just going to put it in 2, 4, 5. So there it is. I have two of these because that's the third place value. So I've got two 256s. And I'm going to add to that 4 16s. And I'm going to add to that 5 1s. So 256 times 2 is the same thing as 256 plus 256, right? So that's 512. So I've got 512 plus 4 times 16 is 40, 50, 64 plus 5. So that's 9, 10, 11. See what I'm doing here? You know how to do this, but I'm trading in 10 ones for 1 10. Right? That's what I'm doing. 6, 7, 8, and 5. So 245 base 16 is the number you know as 581. So let's do one more here. 40A. A, remember, A is 10. B is 11. C is 12, all the way to F, which is 15. And then you regroup at 16. So I'm going to put this in here, 40A. So I have 4 256s. And then just 10 ones, right? So 4 times 256, this is getting to be calculator area. 24, 1, 2, 22, 1, 2, 8, 10. 1024. So I have 1024 plus 10, which is 1034. So 40A base 16 is our number 1034. So it's the same thing. You just got to kind of recall these things, which is pretty simple. So you want to have read this 118, and if you haven't, you can hit pause here and look it over, right? Now we're going the other way, from a base 10 number to a base 16 number. So 1.18 example has two examples, and there's the second one right there. So I am going to do 118A right now. Okay, so we're going to do 571 and base 10 converted to base 16 and 16 and base 10 and converted to base 16. This is a lot like just simple division, but I'm kind of like doing it a little differently, but it's really simple. So I'm going to look for, is there any of these in 571? The answer is no. Is there any of these? No. Is there any of these? See, I'm just working my way down. Well, one of these is 256. That's more than 256. Can I get two of these in there? Well, that would be 256 plus 256, which is 512. Yeah, I can get two of these in there. Can I get three of them? No, but I can get two of them. So I'm going to take 571, and I'm going to subtract the 512 that I already have right now, right here. And I'm going to get that's 9,559 left. So if I just put two zeros here, that number would be 512. But I don't want 512, I want 571. So I need 59 more numbers. So let's go to 16. How many of those can I get in 59? Well, 1 16, 2 16s, 3 16s, 4 16s. I can't get 4 16s, but I can get 3. So I'm going to put a 3 here. 3 16s is 48. And I have 11 left. Recall 11. What am I going to put here? And if you answered B, you would be entirely correct. So that's 2, 3B, base 16. Now I'm just going to do 16. Well, one of those. That's it. So I need the place value here. So base 16, the number 16 in base 16 is 1, 0. Base 16. So you actually may run into these hexadecimal numbers when choosing colors for computer graphics. The colors scheme lists hexadecimal numbers to represent the amount of RGB, red, green, blue. So each of these colors is some kind of combination of red, green, and blue. The table shows 3 hexadecimal numbers and 3 base 10 representations of that. So I'm going to blow this up so you can see how it is made. So you're looking at one section of that diagram, blow it up so we can take a better look. So here's white, which is FF. FF is 255 because it's 15 in the 16th place and 15 in the 1st place. And if you do the math, that'll be 255. So that's red, green, that's everything is on. Red, green, blue, on. Whereas you come down here, it's like this deep sky blue. It's 0, 191, 255. And the digits would be up here for base 16. So that's no red, green, a lot of green, but blue is totally on with some green added, but no red. And so that's kind of how you read that. And it's really just FYI. Some of the chart we just looked at, white is all colors on full, which would be FF. And FF, like I said, is 255, so that would be 255, 255, 255. That's everything on. You get white. And black is the absence of color, which is 0, 0, 0, 0, 0, 0. So is this color number closer to orange or violet? Well, you have to translate this into each color. AE represents red, 2-1 represents green, and F3 represents blue. So the red, which is AE, would be 10 16ths, and E is 14. So that's 10 16ths and 140, 174. So that's the amount of red that you're getting. Green is 2, 1, which is 2 sixteenths, and 1, 1, which is 33. And blue is F3, which is 15 sixteenths, because F is in the second place value. And 3 ones is 243. So with lots of reds and more blue than green, it implies it's closer to violet. Now we're going to look at this one. Example 119A. And we're going to try to discern whether this color is closer to red, green, or blue. Using DEB8, that one. So we're going to do that. And our last question is going to be what color number and color is halfway between here and here. All on white and all off black. You might want to make a guess on that. So we're going to look at this color here, and we need to turn it into our numbers. This is 3 different colors. So DE is red. B8 is green. And 8-7 is blue. So which one is it closer to, red, green, or blue? We're going to see how much. Well, first of all, these are base 16. We're going to turn these into base 10 because the chart has base 10 on it. So remember, A is 10, right? 0 through 9, and then A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So DE is going to be, I'll put it right here, DE is going to be 13 sixteenths. So that's 13 times 16 plus E is just 14 ones. So 13 times 16 is 208. And how did I do that so quick? I multiplied that in my head like that? No, I cheated. I used a calculator on the side. So that's 222. So that's a lot of, because 255 is the max. So that's a lot of red. Green would be B, which should be, I'll put it here, B8. So B is 11 sixteenths. 11 sixteenths, 11 times 16s plus 8. 8 ones. This one I might be able to do in my head. And again, I might not. I'll cheat. 176 plus 8. I'm not going to ask you to do this like this without a calculator. That's not what it's about. So that's 184. And the last one is an 8-7. So 8 sixteens and 7 ones. It's 8 times 16 plus 7 ones. And I don't even like doing that in my head. 8 times 16 is 128 plus 7. That's 135. So this color is closer to red because it's got more red in it than the other ones. So our last problem is what color is halfway between white, which is all colors on, and black, which is all colors off. So an F is 15, or an FF would be 255. How do I know that? Well, 15 sixteens plus 16. But 256 is I know that 256 is 100. 256, so this is one less than that. So divide that by 2, I get 128 about. So I'm looking for a 128, 128, 128. So let's go over the color chart and take a look. So here's our color chart, a little hard to see, but here's 255, white all on, and down here, down on the bottom, second column, is 0. And so we're looking for like 128, 128, 128. And it looks to be like it's going to be right here. See where I am? I'm circling it. And that would be gray, which sort of makes sense, right?